Lester, Wushu engineer. The first video that I ever uploaded to my channel was a video detailing the design, construction and testing of my titanium kukri, also called prayer. I tried to cram a lot of information into that video about construction, testing, fighting tactics, so I believe that I may have lost most of my audience in the complexity and failed to actually concisely convey the true novelty of the approach presented in that video, and incidentally in this one too. So I'm going to go at it a second time and hopefully get a better message across. The true novelty in this video represented here just right off the bat is not the materials used in the construction of the kukris themselves, or the modifications, necessarily the modifications made to the blade profiles, but is in fact that the kukris that I'm going to be trialing here represent a new combined weapon system that makes use of both the kukri and its sheath in combat. I believe that I may lose my viewers in this video as well, because I have a lot of information to present, and this video is going to be ridiculously long, possibly one of the longest videos that I've ever put up on my channel. I might also add that with the ridiculously long video, there was a ridiculous amount of time that I spent actually putting this video together, including building the weapon, testing it, building new testing methodologies. There's a lot of stuff that had to be done. So I'm hoping that you give this video a chance, because I believe that there is real merit to the combined kukri sheath weapon system design. I believe that there's a lot of scope for knife makers, martial artists, reenactors, other enthusiasts to build the system described in this video using a host of base materials and to adapt, expand upon, use the system, experiment with it, come back to me, tell me your take on it. I think there's merit to it. I think the community can actually mine this concept together for those who are interested. If you can't be bothered to listening to me drone on and on in this video in terms of the minutiae that I'm going to be covering, please use the video chapters to at least check out the design discussion points and potentially also the fighting methodology, the fighting approach. So, despite my channel's roots, it's actually been some time since I designed, built and tested a new weapon on my channel. I've spent a lot of the time, and I will be spending a lot more time actually, assisting the Wushu scientist in her studies by developing new testing protocols, training protocols and other testing equipment. So it's probably high time for me to get back to the roots of my channel. But before I begin this video proper, I need to give credit where credit is due. I need to thank one of my American viewers, Jonathan Chalk, for the inspiration for this particular knife, as well as for his valuable input into the construction of the knife as well. I can honestly say that if it wasn't for him, I would probably not have started on this project at all. At least not now. I used quite a few of his ideas in the build process. I adopted much of his input in the design process, and I valued his encouragement. I've been in pretty regular communication on and off with him over the last few years. He is quite like-minded in his love for traditional Oriental martial arts, and also has a strong interest in making traditional weapons, redesigning them for modern contexts, using modern high-tech materials and construction techniques. About a month ago, I was chatting to Jonathan about one of his latest projects, which I'm incidentally quite keen to see taking shape, Jono mate. And during this conversation, I mentioned that I was thinking about redesigning the rondelle dagger and building a modernized tactical version of the iconic medieval armor-piercing sidearm blade. My preferred combat knife design is the kukri, which excels at cutting in an unarmored context, but doesn't do so well up against armor. I was lamenting the fact that you couldn't have everything in one beautiful kukri-shaped package, when Jonathan made the following comment. Well, I decided that was a damn good idea and worth pursuing and testing. So I got the 40-knot wind of inspiration blowing up my kilt, and I immediately got at it in the workshop, despite some pretty high Aussie Christmas temperatures. Before I launch into a brief chat through of the build process, though, I need to chat about the design and the theory behind the knife. As I mentioned before, I wanted a kukri that could function both in a cutting and a thrusting method. So I could easily cut with it, I could easily thrust with it. Matt Easton from Scholar Gladiatoria recently put up a video comparing the kukri design with the Fairbairn Sykes commando dagger design. And the video is entitled "The Best Fighting Knife, World War II Fairbairn Sykes FS Commando Dagger versus Gurkha Kukri." I enjoy Matt Easton's content, and this video is no exception. However, he made an observation during the video about kukris not being optimally designed to thrust with, which I believe was a bit too broad of a generalization. Hashtag not all. The Wushu scientist and I both, or each own a traditional kukri made in Nepal by a traditional kami and sold by a company known as Tora blades. I own the Tora British Service issue, 1970, and the Wushu scientist owns the Tora World War Military Sirupate. Tora Blades actually has a YouTube channel, Tora Kukri, which I recommend checking out. They are also active on Facebook via a group called Tora Kukri. I wholeheartedly recommend their knives, the knives themselves. Our knives took a bit of time to get to us because they were handmade to order, but they were absolutely well worth the wait. If you are interested in owning a traditional kukri, I would strongly recommend that you consider Tora Blades. Tora Blades kukris, I believe, have been designed to be identical to some of the original patterns issued during various conflicts and historic periods. One thing that stands out when you compare Tora Blades designs with many modern kukri recreations is that there's a continuous banana curve of the knife which flows into the handle itself. I'll just draw the Wushu scientist's kukri and show you here, and you'll be able to see. I'll also have some photographs up how the curve continues seamlessly into the handle. Often you'll find kukris that have been designed with the iconic curved blade that eventually morphs into a completely straight handle, which is in line with the top spine of the knife. The straight handle design is possibly more suited for and specialized for cutting, while making thrusting movements uncomfortable and inefficient due to the position of the hand and the wrist when thrusting forward with the knife. A continuous curve through the kukri, like this one for instance, allows the user to thrust very effectively because the reactive force of the thrust impact is transmitted effectively into the palm of the hand and then into the long bones of the forearm without placing much in terms of lateral forces into the wrist joint, either up or down. I do believe that this is an ancient intentional design criterion to produce a knife that excels at cutting but also functions reasonably well at thrusting. It's a bit genius, really. You can even see that intentional design feature in the way that the handle of the kukri is designed. There is a concentric main raised ring in the center of a traditional kukri handle, which is designed to fit in between the middle finger and the ring finger. This is often explained as helping to prevent the hand from slipping forward onto the handle, because as you can see, traditional kukri designs typically do not have a hand guard. However, you may notice that the handle of this kukri, the Wushu scientist's Tora military sirupate, has a different handle diameters and profiles on either side of the central ring. This is a design feature that's not often discussed. On a handle that follows the blade's continuous curve, the larger handle diameter closer to the blade, combined with a smaller diameter handle part towards the ring and pinky finger, also helps to direct thrust impact forces into the palm of the hand. So essentially it kind of lodges into the palm there. So transmit those forces safely into the wrist and the long bones of the forearm, as mentioned previously. I have seen many historic examples of kukris that do not demonstrate these design features and have straight handles that do not follow the curve of the kukri blade. So I don't believe that this is necessarily a feature of fake or modern kukris, so that's not what I'm saying here. However, kukris with a straight handle that do not possess this continuous curve along with the specially designed handle are indeed very difficult to thrust with and can place very uncomfortable lateral forces on the wrist during thrusting, as Matt Easton states in his video. Our Tora blade kukris, however, allow very forceful thrusting and stabbing without placing any undue stress on the wrist joint. In fact, I personally find it more comfortable to thrust using this kind of kukri than I do with a straight blade and straight handled knife, because of the angle that I can hold my wrist at. With a kukri, because of the point being sort of out there in line with the palm, I can keep my wrist at a more comfortable angle. Whereas if the tip is in line with the spine of the blade, I actually have to bend my wrist forward a lot more in order to get that thrusting movement right, which I find can be quite uncomfortable if you're thrusting quite hard. Of course, there are many other ways to thrust, but if it's a typical forward thrust like that, it does place a little bit of additional strain on the wrist. So because I wanted to build a thrust-centric tactical combat kukri, I adopted many of the design features of the Wushu scientist's sirupate, the Tora blade's sirupate, including the curve that continues into the handle, the thicker foregrip, special middle ring profile, and thinner or narrower hind grip. However, the typical sirupate blade profile was still too wide near the tip to allow for the level of thrust specialization that I wanted. So I took the Wushu scientist's sirupate blade dimensions and profile as a template and then modified it. I reduced the blade width near the tip by approximately 20% and added a cross guard to aid in weapon fencing and manipulation, and also in thrusting. I did not incorporate the traditional choke notch in my design because I was concentrating on a minimalist, practical, modern, tactical design. Possibly my most controversial hot take of an idea for this design was that I decided to build a knife out of 4mm thick Hardox 450 steel. For those who don't know, Hardox is a pre-hardened industrial steel. However, it's not as hard as the types of steel that most knife makers recommend as good steel for making knife blades from. In fact, some folks would argue passionately that you can't possibly make a functional knife from steel below a certain hardness. I guess these people do not believe that for most of human history, including large periods during the Middle Ages, humankind did not have access to steels of the required hardness and yet still managed to make perfectly serviceable knives and even swords. The consistency, tensile strength, and even the hardness of Hardox 450 would make it superior to most of the weapon steel used during most of our human history. Anyway, I'm not going to fight about steel choices. I may be a nerd, but I'm not the kind of nerd who chooses to die on lonely hills on the internet. I've got far more constructive things to do with my time than engage in pointless arguments. I don't have a forge. I don't have the know-how to use one or the inclination to learn how to forge steel, but I had a sheet of 4mm thick Hardox, and so that's what I used. Will the knife made out of Hardox require more regular sharpening than a knife made of harder steel? Certainly. Will that make one iota of a difference in the heat of combat? Nope. As mentioned, in order to facilitate more efficient thrusting and stabbing, The blade width was substantially reduced towards the tip by approximately 20% as compared to the template that I traced around the Tora blade's military sirupate. However, I decided that the tip would retain the 4mm thickness of the blade right up until the last centimeter or so of blade length to ensure that the tip was robust enough to pierce through hard materials like mild steel without bending or breaking. In addition, the handle was shaped as described earlier, with a central ring dividing the two halves of the handle, and with a larger diameter section corresponding to the index and middle fingers, and a smaller diameter section corresponding to the ring and pinky fingers. This would work to convey forces more efficiently into the base of the palm, into the long bones of the forearm, without placing too many lateral forces on the wrist. The cross guard would also function as part of the thrust modifications, ensuring that if the hand did slip during a thrust, that it would encounter the guard instead of slipping down onto the blade. As well as helping with the thrust, the cross guard would provide some small tactical benefits if the curve of the kukri, I'll use mine, if the curve of the kukri was used to hook and manipulate other weapons, perhaps in a very temporary bind. In addition, it would prevent other weapons so manipulated from easily sliding onto the hand. The most important defensive modification of all was the design of the sheath to function as an offhand defensive bracer or buckler. Kukris typically come with rigid or semi-rigid sheaths made of wood and leather, like this one, for instance, which is the sheath for the Wushu scientists' Tora blade's sirupate. These sheaths are necessary to protect the knife from the elements, as well as protecting the wielder from accidentally injuring themselves from contact with what is quite a large and sharp cutting surface, or cutting blade, I should say. However, apart from this basic protective function, they provide no real benefit in combat. So once in combat, traditional kukri sheaths are essentially useless dead weight. As with my titanium kukri, I wanted the sheath to be functional within combat as a bracer for the offhand, as I'll demonstrate here now by just putting on the sheath from my titanium kukri. This could then be used to protect both hands and wrists from direct attack. So Crescent's sheath was designed to provide protection against significant cutting, chopping, and penetrative forces through the use of multiple layers of G10 fiberglass laminate. This tactical sheath can then be worn in the offhand using a flat strap handle that still allows the user to grasp and manipulate objects with that hand. In order for the sheath to be viable as an offhand defensive weapon, the whole system has to be designed for speedy deployment. I found that the best way to achieve this, as with my titanium kukri sheath, was a quick release snap buckle. You can see the one section of it here. This allows the whole knife and tactical sheath system to be quickly released from where it's held on a belt loop or wherever it's being held, slipped into the offhand, and then the knife drawn out of the sheath with reasonable speed. I don't always like lanyard straps, but they can perform a valuable weapon retention role when under pressure. So hence the inclusion of a lanyard strap attachment point, as in my titanium kukri here. Of course, caution should be applied when using them, because if the weapon is effectively captured, the lanyard strap can also be used to manipulate or injure the wearer. This is less of a problem with edged weapons because of the difficulties involved with capturing them and manipulating them safely. The lanyard strap attachment point can also function as a percussive focal point and can be used as a glass breaker in a pinch. I like kukris that are designed with the point of balance closer to the handle for more deft movement. In this case, because I was going to be incorporating a full tang that followed the shape of the handle, there was a lot of steel behind the blade in the grip. This made for a heavy blade overall. So ultimately, ultimately Crescent turned out to be the heaviest kukri by far, at 648 grams. But it doesn't actually feel heavy at all because of the point of balance. I'll just take it out of its sheath there, trying to balance a whole bunch of kukris on this table in front of me. So this is Crescent. Even though it's quite heavy, it doesn't feel heavy because of the point of balance being quite close to the handle. It actually feels quite deft. So it feels nimble, feels alive, can easily strike and cut with a great deal of authority. Now, the inset picture shows a comparison of the locations of the centers of balance for Crescent, my titanium kukri, the Tora blade's military sirupate, and the cold steel kukri machete. As you can see, both Crescent and my titanium kukri have centers of balance that are a lot closer to the handle than typical kukris and kukri derivatives. So onto the construction process. I cut the basic shape out of my sheet of hard ox using a bandsaw, and then left the cutout in vinegar overnight to remove the hard ox surface oxidation. I then did some rough grinding using an angle grinder. I was very careful about that because, of course, if I overheated the steel, it would lose its hardness. After finishing with the angle grinder, I finished grinding and basic polishing on a belt sander. So as I mentioned, I was quite concerned in the beginning about overheating the steel during the grinding process and softening it by accident. That's why I actually did most of the grinding and finishing on the blade before even starting on the handle. I was careful to, just in case I completely stuffed it up and had to try some last ditch heat treatment of my own, which would have been a complete flop, so I'm glad I didn't have to do that. I was pretty careful to monitor the temperature of the steel while grinding, wetting it down with water frequently, and fortunately I didn't run into any problems, so that was good. I did not give the knife a distal taper, as you will be able to see from top down. It's fairly uniform, 4 millimeters thick right up until the very end. Because Crescent was going to be used in thrusting and stabbing, perhaps into hard armor, I made sure that the tip was quite robust and not too thin by leaving that 4 millimeter thickness all the way right up until the last centimeter or so. As a basic observation, even though the Hardox 450 steel is slightly harder than the grade 5 titanium that I used to make my titanium kukri, grinding it down was an absolute breeze in comparison to grinding titanium. Titanium is an absolute beast. It's hard to grind down, and it eats up sanding belts and essentially renders them useless after really just like half an hour of it. Essentially, you've got a dulled sanding belt. After doing the grinding on and finishing on the rough finishing on the blade for Crescent, I wrapped the blade in paper and masking tape, and I went to work on the handle construction. I used built-up layers of black G10 fiberglass laminate to make up the handle scales. Once they were epoxied together, I epoxied them and clamped them onto the steel knife handle section using concealed tension pins as fasteners. Thanks to Jonathan Chark for the suggestion for the fasteners, by the way. Once the epoxy had set, I went to work grinding down the handle scales to shape using an angle grinder, and then polishing them on the belt sander using various grits. I finished up work on the handle using a Scotch-Brite belt as well. After the handle was complete, I went to work building the tactical sheath or bracer. The sheath bracer is meant to be able to survive a significant slash, cut or impact, so it must be built out of robust materials, but must also be very light, so as not to be a burden in combat or if you're just bearing the knife in its sheath in normal day-to-day activities. My titanium kukri sheath bracer has a layer of 2mm thick titanium in it, which provides pretty massive protection and is a bit of an expensive overkill to the design, really. In Crescent's case, I opted to use G10 fiberglass laminate along with some aluminium structural elements, which you'll be able to see here. So these are the aluminium sections along the side, and these are the G10 fiberglass sheets. I used 2 layers of 3mm thick G10 for the main sections, along with 6mm thick aluminium side walls. This represents a minimum of 6mm of G10 that a weapon would have to break or cut through in order to breach the bracer defense directly, which would be more than sufficient to stop most weapons in their tracks. I epoxied the leaves of the sheath bracer together under pressure and riveted them in place for additional structural integrity. The strap handle and snap buckle fixing strap, as you can see here, were made using 1mm thick sheet of black Grilamid riveted onto the G10. You'll also notice that there's some high density foam padding as well, some thin foam padding there just to make it a little bit more comfortable to wear and to protect the hand from impacts to the surface of the sheath bracer. I finished the sheath bracer off with an aluminium moon crescent to represent the weapon's name. As of the making of this video though, I'm still waiting on the metallic snap buckle to arrive via mail order, so you'll see that there's something missing here. Once the knife and sheath bracer were complete up until this point, I treated the knife blade with a steel bluing compound, again thanks to Jonathan Chalk for recommending the manufacturer. So as you can see, the blade has been blued. The product that Jonathan Chalk recommended was Birchwood Casey Super Blue, which worked really well actually. Partway through the build process, the Wushu scientist subtly indicated that she wanted the knife as a Christmas present. So the knife's ownership switched hands midway through the build. Now once the knife and sheath were complete, I decided to put it through some fun tests first. Some of them a little bit abusive. Starting with some basic coconut cutting. Please note that we do not waste food on the Wushu Engineer channel. All coconut flesh was harvested, grated, dried and toasted in the oven and will go into the Wushu scientist's excellent granola. As you can see, as you'll be able to see from the footage, Crescent performed reasonably well at cutting coconuts. Okay, so this time I'm gonna slash that back. However, Crescent was designed for stabbing as well, so I tried a couple of stabs into thrown coconuts. Now this is not as easy as it sounds, because you have to the coconuts are not soft, they're hard. You have to line the tip of the knife up with the center of mass of the coconut, and you need to direct your thrust appropriately, or the coconut will just bounce off the tip, the edge, or just spin in the air. Still, I managed to get it right a couple of times. There you go. Thank you. How's that? Again. Right.
Got it. Got a big chunk of it.
Yeah. That was awesome.
Yeah.
Okay, stop. I then decided to test Crescent by stabbing through some standard corrugated galvanized roofing steel. Note here, note that my disclaimer before I get roasted in the comments section. I am very well aware that this is mild steel and it's only about 0.5 millimeter thick, and so I don't need to be told that it's not representative of high quality historic armor in any real way. I already know that. However, it does represent a fairly abusive test for a knife, especially for the tip and the edge, and that's the way that this test should be viewed. It's merely an abusive test to see how this design fares as a stabbing instrument.
Cicada, obviously just hatched out of his larval stage after the long sleep underground, joining us for my stabby tests. I hope I don't disturb him too much. So I got a piece of roofing steel, old roofing steel here, some mild steel, galvanized, standard roofing steel. So we'll see how this particular kukri design stands up to stabbing into sheet steel. It wasn't particularly energetic, but as you can see, went straight through, cut into it quite deeply. Try it again. Quite nasty. It's maybe about 6-7 centimeters deep. I'll try one more time. Added a bit of an angle there. Very nasty. Yeah, that's not something you're going to walk away from. That's over 10 centimeters deep. So let's have a look at the damage on the knife. No damage to the tip. Some blemishing on the blued steel finish. The edge is actually still serviceable. I'm not sure if you can see that. Edge is still serviceable. No real degradation there. So yeah, I'd say that's quite compelling.
As you can see from the tests, it was fairly easy to stab through the roofing steel. In addition, the tip experienced no damage at all, while the edge was only slightly dulled from cutting through the steel. Even the blued finish was only mildly scuffed, not even badly enough to warrant repolishing and treatment. There was no scratching of the blade, nothing. This could be down to the abrasion, the stated abrasion resistance of Hardox 450, as reported on the Hardox data sheet. So from these more sort of fun and less objective tests, I went on to try to do something a little bit more scientific in terms of testing cutting performance. As you can see from this, from a snapshot of this YouTube poll I posted over a year ago now, I have been intending to develop a scientific and objective test for weapon cutting performance for a very long time now. 83% of the voters agreed that I should
Do it! Just do it!
Well, all the stars aligned for this video, and the idea coalesced in my head and made it into this video in time. I intend to upload a dedicated follow-up video, or maybe even more than one, discussing our new impulse cut method for measuring weapon cutting performance at a later date. So I'm not going to go into too much detail in this video. Call this a quick trial of the method if you like. Briefly, the impulse cut method is based on our impulse block method for measuring human striking characteristics. The impulse block method allows for one of the most comprehensive analyses of human striking available currently to our knowledge. Our impulse block method has been independently tested for validity and reliability as part of a study by the University of Southern Queensland. In a nutshell, the impulse block equipment consists of a specially designed foam spring called the impulse block, attached to the front face of a load cell that records force input. Using the measured values from the load cell, it becomes possible to calculate a number of characteristics associated with the impacting object. The primary characteristic of interest in this case, however, is impulse, or change in momentum imparted by the strike. For a more detailed explanation of the impulse block equipment and methodology, you can see some of my other videos on the topic. The impulse block method can also be adapted to measure cutting efficiency, and in this case we call it the impulse cut method. The impulse cut method involves adapting our impulse block method to measure impulse associated with cutting through a sample card of a particular material or medium. In this case, the chosen medium was a 9mm thick MDF board, or medium density fiber board. As you can hear, it's quite solid. Is used in construction, not as load bearing, but often as wall sections, that kind of thing, in some furniture construction as well. This card was fixed to the front face of the impulse block, and a cut was performed into the edge of the MDF card. The cut depth was then measured and used in the calculations. Impulse and impact duration were calculated using the force time data from the load cell. Once we had the impulse, impact duration and cut depth associated with a particular weapon, we could take these values and calculate the energy involved in the strike, as well as the energy per linear meter associated with the cut. These values could then be compared between weapons to ascertain which weapon cut with the least amount of effort or energy committed to the cut. One of the limitations of this testing methodology is the type of medium that the cuts are performed into, in this case the 9mm thick MDF board cards. This will of course have its own characteristics that may favor some weapons over others. So it should be noted that all the measured and calculated values associated with these tests are specific to the type of medium used in these tests. Using a different medium, such as ballistic gelatin for instance, would more than likely yield different results. No scientific test, again, would be complete without mentioning the sources of error. There are measurement errors associated with all pieces of measuring equipment and measuring methods. The equipment used in these tests has been calibrated, and repeated drop tests have been performed to ascertain the percentage error associated with the impulse block method as part of the studies that we are undertaking in collaboration with the University of Southern Queensland. Based on these drop tests, our impulse block method is accurate to under 10%. In other words, the error associated with the method is less than 10%. In addition, I was careful to measure the cut depth in the MDF cards. There is the potential for error there, although it would be pretty small because the cuts were measured several times over. Lastly, we should also acknowledge that an extremely small sample size was used in this case. Only a single cutting test was performed per weapon. This can lead to very significant errors. However, as mentioned earlier, consider this a simple first trial of the impulse cut method. And after that brief discussion of the methodology, this is what the tests looked like. So welcome to the official testing part of the video. I'm going to be testing four knives today and comparing the results between each of them. Each of these knives, well, the knives in order, in no particular order, I'm going to be testing the cold steel kukri machete. I'm going to be testing my titanium kukri, also called prayer. I'll be testing the Tora blades military sirupate, which belongs to the Wushu scientist. And I'm going to be testing, of course, the Hardox steel kukri, which has been optimized for thrusting and has a number of other modifications on it called Crescent. Each of these knives, I've sharpened each of these knives using a sharpening steel. So they may not be shaving sharp, but they're all roughly the same sharpness. Possibly the because of the hardness of the steel used in the Tora blades military kukri, military sirupate, this is possibly the sharpest of the bunch. But they're all fairly close. They're all roughly paper shaving sharp, including the blade Crescent, which is the primary knife that we're going to be comparing with the performance of all three. Behind me is the setup that we're going to be using. We've got our impulse block set up over there. I've built a specialized front plate that allows the mounting of these MDF cards. They're fairly thick, about just under a centimeter thick or so. Each is labeled, of course, with the knife that's going to be tested against it. Each knife will be, I will cut only once with each knife into the very edge of the MDF card, and we're going to be measuring the impact forces using the load cell, also extrapolating momentum, and then we're going to be doing a bit of processing to see which of the knives cuts deepest with least effort. So in other words, it's how expensive in terms of energy and momentum transferred into the swing of the knife, how expensive is the depth of that cut. So in many of these kinds of tests you can find that perhaps there's a subconscious bias towards one knife or sword or over another, and because of that subconscious bias, the person doing the testing may subconsciously swing harder with one than the other, and so it becomes a little bit unfair because the one that cuts deeper, perhaps they put more effort into. So this is going to keep a track of how much effort I'm putting into each swing. So it should give a fairly scientific, fairly objective measure of how easy it is to cut using each of these knives. And we'll see what we get at the end of the day. My predictions, I haven't done the tests yet. I actually believe that the cold steel kukri machete may cut deeper than the others with less effort, purely because the blade itself is very thin. It's only about just over 2, maybe just under 3 millimeters thick. Whereas the next in line in terms of thickness, of course, is the Crescent, which is only 4 millimeters thick. But then the other two kukris, the titanium kukri and the Tora blades military sirupate, they are fairly traditional in that the blades are very thick. So these two are going to struggle, I think, to penetrate, to cut into the material that I've chosen as a test medium, which is the MDF board, purely because of the thickness of the blade. But we'll see what happens. I believe, as I said, that the cold steel kukri machete will actually cut deepest with least effort. I think it may be followed by Crescent, followed in third place by the
the Tora Blades military sirupate, and then finally I think my titanium kukri is going to struggle because it's quite thick, and of course the blade is very light. That has advantages as well, of course, but that's more in actual combat in terms of speed of reaction and speed of cut and thrust. But in this kind of objective cutting test, where we're only looking at cutting effectiveness, I think this is going to come last. But we'll see what happens. Each of the blades has been treated with a PTFE, which is kind of like a Teflon-based dry lubricant, to ensure that each knife has the best possible chance of passing through that material with least effort. So we'll go on now to the tests, and we'll see what happens. I'm actually quite excited to see what happens. Okay, so test 1, the cold steel kukri machete. Just say when.
Okay, when you're ready.
Right, so next is the titanium kukri called prayer. Just say when.
Okay.
Next is the Tora Blades military sirupate. So when. And last but not least is Crescent, and we'll see. Okay, so when. The results got really interesting for these tests. Let me remind you here that all measured and calculated values associated with these tests are specific to the type of medium used in these tests, 9mm thick MDF board cards. If we were doing a simple which knife cuts deeper test, as commonly performed here on YouTube, in backyards the world over, the clear winner would be the Tora Blades military sirupate. So I was actually quite wrong in my initial predictions, because I thought that the cold steel kukri machete would cut the deepest. The Tora Blades sirupate, which cut the deepest, was followed by the cold steel kukri machete, then by Crescent, and finally my old titanium kukri. At first this seemed to confirm my prediction that the titanium kukri would be the poorest cutter due to its low weight and its point of balance that is closer to the hand than typical kukris. However, when we completed the calculations and looked at the energy required to perform the cuts, and in particular the energy required to cut per linear meter for each knife, things got really interesting and a little bit non-intuitive actually. As you can see from the table, the poorest performer in terms of energy to cut per linear meter was the cold steel kukri machete at 344 joules per meter. The Tora Blades military sirupate and Crescent were pretty close at 314 and 301.9 joules per meter respectively. So despite the fact that Crescent has been designed specifically to favor thrusting over cutting, it can still cut very efficiently and very deeply as well, rivaling the performance of the cold steel machete in terms of deepness of cut, and having a very similar cutting efficiency to the Tora Blades military sirupate. Defying all expectations though, the titanium kukri prayer beat all the others in terms of cutting efficiency by a mile at only 257.2 joules per meter. So how do we interpret this data point? Well, basically, although the titanium kukri did not cut particularly deeply compared to the other kukris, perhaps due to the mass and weight distribution of the weapon, it required far less energy to cut with than with the others. Strangely, this result somewhat backs up the simple cutting tests that I performed all those years ago in my original titanium kukri video, which seemed to indicate that it could cut at least as well and possibly even better than a similar steel kukri. I'm still profoundly weirded out by this result, and I'll be thinking about it for some time. Perhaps we need to do more tests to confirm. I think that performing more tests like this may provide data sets that could help in the design of more futuristic types of knives and swords, incorporating more advanced blade profiles and advanced materials like composites or advanced metals. Perhaps if sufficient data points are retrieved from tests like this, a model can be derived that could form the nucleus of an AI design program that could come up with knife designs that would defy the imagination but cut in superior and more efficient ways. Now, adding what is essentially a second offhand defensive weapon, the kukri sheath, in addition to the kukri, will of course mean that full weapon system deployment time is extended because you are having to draw and ready two separate items instead of just one. So I decided to test the time difference between drawing and readying my titanium kukri and deploying the full titanium kukri and sheath system. And this is what those tests look like. So what we're going to do is to just measure the difference in time that it takes for me to deploy the whole system, so the sheath and kukri as a combined fighting or combat system, as opposed to just simply drawing the kukri and fighting with it. And clearly there's going to be a time difference because one is a more complex set of movements than the other. And in this case, I am just using the shoulder slung underarm mounting strap, if you like, with my titanium kukri. The snap buckle for the Crescent kukri has not arrived yet. We've mail ordered it. I want one of those metallic style quick release snap buckles. This has just got a plastic snap buckle on it, but it will serve to illustrate, at least it'll give us some information to go on as to how long it takes for each of these to be done. Of course, the snap buckle can be attached to a similar snap buckle on a belt loop, but I don't have one of those set up just now. I just have the shoulder strap because it's just convenient to sling over the shoulder if I'm going for a bushwalk or something on my property. So we'll see how long it takes. So first of all, I'm going to just do a few tests where I'm just drawing the kukri, okay, and going into a combat stance. So let's test one. Test two. Test three. Test four. So we'll just do 4 tests with each method. So now we're going to see what the full deployment looks like. Let's test 1. Test 2. Test 3. Test 4. Okay. And we'll see what happens, we'll see what those values are like. As you can see from the footage, there was indeed a time difference between the simple deployment and the full knife sheath bracer deployment, as you would expect. However, the difference between the two was not as much as you might expect, and was actually less than what I anticipated. I anticipated that deploying the full system would take about 3 times as much time as just simply drawing the kukri. The average time for the deployment of my knife alone was approximately 1.47 seconds, while the average time for a full knife sheath deployment was 2.91 seconds. This represents a 97% increase in time to deployment, so a little less than double the time to deploy the full system. If the situation allows for it, the tactical and defensive benefits of deploying the full knife sheath fighting system would certainly justify the additional time. Alternatively, the full kukri sheath system, I'll just quickly demonstrate what I'm about to say. The full kukri knife sheath system can actually be worn in the offhand like so. The handle is fairly tight, so it's not going to fall off my hand. So this can be worn in this way if a use case is expected. The offhand can still be used to do basic tasks while the knife is being carried in this way due to the flat strap handle, which doesn't interfere too much with the grip. That way the system is carried already half deployed, and the full deployment will take no longer than simply drawing the kukri from its sheath. I believe that many of my viewers are familiar with some form of knife fighting or another. So I'm not going to get into too much detail about knife fighting techniques and risk preaching to the choir, so to say. Suffice to say here that one of the prime targets in a weapon fight is the hand that wields the weapon. Because of the fact that in order to use the weapon, this hand and wrist has to come into fairly close proximity with an opponent, typically, in order to wield the weapon. This core idea has spawned many tactical and strategic mitigatory methods, as well as defensive weapon evolutions, such as elaborate basket hilt guards on fencing swords. In fact, Matt Easton recently posted up a video on this concept on his Scholar Gladiatorio channel, which is common to most, so the concept is common to most weapon-based fighting systems, including our own. And this video is entitled Bowie, Big Knife and Bayonet Fighting, Take the Hand, Lessons from Biddle, World War II. While I'm chatting about the combat techniques, I'll have some basic sparring footage playing in the inset screen to show some examples of the kukri sheath fighting system used against a superior reach weapon, a jian in this case. Although the approaches shown in the sparring segments would change based on the type of weapon being faced, such as whether the reach weapon is impact or cutting based, the basic defensive structure will probably remain fairly similar. As you can see from the footage, I am at a serious disadvantage against the reach weapon, even with the kukri sheath system deployed. The asymmetric threat of the reach weapon also forces me to be a lot more forward moving and aggressive than I might ordinarily prefer to be in that kind of instance. If I were to concentrate on more defensive sparring approach with this kind of weapon mismatch, the results would be disastrous, because the Wushu scientist would just fence until she found an opening, and then it would be game over for me. You can actually see that happening in the longer sparring segments where the Wushu scientist managed to get some space and distance, clearly winning the advantage in those cases. However, despite the fact that I'm clearly at a serious disadvantage, I'm at far less of a disadvantage than I would be with just a kukri alone in my hand. If that were the case, the Wushu scientist would clearly dominate in most instances, even if I was adopting an aggressive forward-moving approach, which I would actually have to in that case as well. As you can see from the footage with a combined kukri sheath fighting system, the offhand is shielded by the kukri sheath, and this hand is placed in front of the hand holding the kukri, typically to shield both hands from direct attack. The line of defense thus created by the kukri in the sheath is typically brought into the fighter's center line and forms a very effective defensive structure or barrier that can be moved as necessary to intercept attack vectors. This guard position is actually derived from our basic Kung Fu guard position, which looks a little bit like that. Here the arms and the hands protect the center line of the upper body as well. This type of guard is typical to many different types of combat systems. So this guard position forms the basis, the foundation of the combat concept in this case, with the kukri playing peekaboo from behind the guard, like so. Of course, this kind of guard cannot be held for long, especially against a superior reach weapon, as demonstrated in the sparring clips. This should not be deployed as a long duration defensive fencing weapon system against weapons of superior reach. This guard position only buys the defender scant seconds and allows for a slightly safer means of entering beyond the reach of superior reach weapons. Aggressive and decided movement must be made to get past the opponent's optimal range into a position where the kukri can dominate. The kukri either strikes from behind the guard to occupy the opponent defensively, or the kukri sheath guard is used as a blocking deflecting structure, as I mentioned before, while you close and move past the opponent's effective minimum range. Once you close with your opponent, the kukri and sheath guard position can be broken to engage at closer range and finish. Perhaps, as demonstrated in some of the sparring clips, using this to manipulate the other weapon while finishing with the kukri at close range. Because the sheath is held in the offhand using this flat strap that doesn't interfere much with grip, the offhand can also still be used to grapple at really close ranges, so it doesn't interfere much with grappling and manipulation. Of course, against inferior reach weapons, perhaps another knife for instance, the kukri can be used at range in more of a long duration defensive fencing capacity, along with defensive boosts provided by the sheath. So there's not much more for me to say in conclusion. I believe that a system like that demonstrated in Crescent or in my titanium kukri prayer, with their tactical defensive sheath braces, is perhaps the future of kukri fighting knives. I have thoroughly enjoyed designing, building and testing this knife. I think it's an absolutely perfect melding of Beauty and the Beast, and so a perfect Christmas gift for the Wushu scientist. I'd love to hear from you if you're interested in building one of these types of tactical kukris yourself, with the, of course, with the tactical defensive sheath. I am also always happy to answer technical questions and assist where I can if folks want to build something based off my designs. I hope you enjoy this video, and I'll see you all again next time. Cheers.